Hello and welcome to the 20th lecture of our course on photonic devices. Today's lecture is the third and final part on this series of lectures regarding laser diodes. And on today's lecture we're going to talk about some more sophisticated types of cavities and structures used in order to obtain single frequency lasers, such as distributed Bragg reflectors, distributed feedback lasers, and VCSELs. So in order to do this, we need to define what is a Bragg reflector or a Bragg grating, okay? And the first type of laser we'll discuss is the distributed feedback laser, the DFB. So a Bragg reflector is a multi-layer structure in which high and low refractive index layers or films are stacked. So for example, you might have something like this, many layers, one given direction, so perpendicular to the direction of light propagation. And usually, these consist of high and low, staggered high and low refractive index layers. So for example, you might have N1, which is a higher refractive index, and then N2, and then N1 again, and N2, and so on, right? So in this case, I chose N1 to be larger than N2. We have this type of structure where the refractive indices alternate through the structure. And if these reflectors are designed correctly, we will have a device that has a high reflectivity, which means that, if you impinge a beam of light with a given amount of power, it's going to reflect almost 100% or 100% of that power for a particular wavelength. So it's going to be a very high reflectivity mirror for a particular wavelength or for a discrete set of wavelengths, right? So if the layers have indices N1 and N2, and the thicknesses of the layers are chosen to be lambda 1 over 4 and lambda 2 over 4, so a quarter of the wavelength in the respective material, and here lambda 1 implies that we're talking about the refractive index inside the media with index N1, and lambda 2, the same thing for the medium with index equals to N2, right? So, and these would be just the wavelength in vacuum divided by the respective refractive indexes, in such a way that lambda 1 is equal to lambda naught, which is the free space wavelength, divided by N1, and lambda 2 is equal to lambda naught divided by N2. And if the reflector is designed like this, it will have a high reflectivity for the wavelength lambda naught, right? I'm talking about, it's the same wavelength, but I'm talking about the wavelength in free space. So for that particular lambda, for that particular wavelength and the corresponding frequency, the reflectivity is going to be high. For other wavelengths, the reflectivity is going to be low, so it's going to be a selective mirror. And it is possible to show that the condition that we've just mentioned, the quarter wavelength thickness for the layers, has to do with the fact that if the layers are designed in such a way, the waves that propagate back and forth through the layers will interfere constructively once they come back to the same medium, to the original medium, right? So for example, let's consider this situation here, and let's say that N1 is greater than N2 in both cases, right? So the beam of light impinges here, and part of it is reflected right at this interface, but another fraction is transmitted to the medium with index N1, propagates through the layer, is reflected back, and then is partially transmitted back to the original medium. So what we're saying here is that if the thickness here of this layer is equal to lambda 1, the wavelength inside this medium, divided by 4, then the phase acquired by the wave is going to be, well, let's say pi over 2 in propagating, you know, across this layer, then in the reflection here on this side, there's not going to be any, if we're talking about normal incidence, of course, there's not going to be any phase shift in the reflection itself, and then you have an additional pi over 2 when the wave propagates from this point to this point. So an overall phase shift of pi, right? But if the index of this medium is larger than the index than n2, then the phase acquired by the wave in this reflection right here on the first interface is also pi. So both of these waves are in phase when reflected back, you know, to the original medium with index n2. And the same thing will happen, you know, if the middle layer here has a lower refractive index, so n2 still smaller than n1, but now, you know, the middle layer here is n2 rather than n1. So what will happen here when the wave is transmitted to the medium with index n2, there will be no phase shift for normal incidence. For normal incidence, it will acquire a phase of pi over 2 as well, so 90 degrees in propagating through the layer. And then because this is a smaller refractive index than the other medium, then what will happen here is that there will be another phase shift of pi, so pi over 2 plus pi, and then another pi over 2 in propagating from here to here, and so you have a 2 pi overall phase shift, right? And the wave that is reflected here, the blue component here, in this reflection, because the incidence medium, you know, has a greater refractive index, the phase acquired is 0. So you have 0 phase acquired at this point and 2 pi phase acquired at this point. These two guys are also in phase. So, and this will happen, you know, if the thickness of this layer, of course, is lambda 2 over 4. So quarter wavelength thicknesses, you know, and of course lambda 1 and lambda 2 are related to a single lambda naught, you know, a single wavelength in free space, right? So in, you know, we see clearly that constructive interference must happen for the reflected wave for this particular wavelength, and therefore the reflectance of the Bragg stack is high for this particular wavelength that satisfy these conditions that are described here. So this is more of a hand-wavy way of discussing the phenomena behind Bragg reflectors. A more proper and accurate approach would be to use some sort of numerical or semi-analytical method in order to calculate the reflectance of the stack itself, right, the stack of layers, as a function of frequency or wavelength, using the transmission matrix method or any other related method, and this can be done very easily. But what we end up having is a reflectance, or, you know, reflectivity spectrum which looks like this, right? For a particular wavelength, which is the Bragg wavelength, the reflectivity is high, and then it falls abruptly as you move away from the Bragg wavelength. Of course, there's, you know, if you take multiples of this wavelength or multiples of these frequencies, you'll have more peaks in the reflectance spectrum, but this is the overall shape of the spectrum, right? So what will happen is that you can have, you know, a beam of light with all wavelengths or a given range of wavelengths, and only this particular wavelength or light with that particular wavelength will be reflected by the stack. The rest, of course, will be partially transmitted or completely transmitted. You see that there are side lobes here, so the reflectivity here, right, is not absolutely zero, but this can be designed to have a very high reflectivity for a for a particular wavelength and low reflectivity for other wavelengths. Okay, now in a DFB laser, in distributed feedback laser, the gain medium is contained inside a Bragg stack, which is fabricated through the use of a corrugated surface, which we'll see in a minute. This is achieved by creating a corrugated structure on top of the active region, directly above the active region itself. And feedback inside the structure will only happen for the Bragg wavelength, which will be the wavelength corresponding to the beam emitted by the laser itself, right? So a DFB therefore would look more or less like this, right? You'd have a grating, a periodic corrugated structure, which is, on this case, the p-type semiconductor here. The period of the grating would be related to the Bragg wavelength, so there are specific equations used to design this grating in order, for the high reflectivity to happen for a given lambda b, or for a given Bragg wavelength. But so you have this corrugated structure here, and light propagates in the active region as we've seen. So the mode is gonna perceive this variation in the refractive indices between the region where you have the peaks in the corrugated structure and the valleys, and therefore effectively it will be as if this structure were similar to the multi-layer film structure that we talked about, although it's not strictly the same thing, right? The fact that you have this corrugated structure here will have the same effect as the multi-layer stack film, because you can imagine that when this transverse mode is on this region here, right, because you have more of a large refractive index material on this cross section here, the effective index is going to be a little bit greater than when the mode is right at the valley, right? So here the effective index and effective, you would expect, if this refractive index here is smaller, right, the effective index here will be a little bit smaller than it is right at this position. Therefore it is as if you had a multi-layer structure with alternating refractive indices. Okay, so all of this is fabricated inside the double heterostructure that we've discussed in our previous classes, right? So you have the active layer here, the p-type semiconductor and the n-type semiconductor up and down here. So the structure has to be microfabricated along with the waveguide inside the semiconductor device itself, right? And this is a picture of the corrugated layer, scanning electron microscope picture, just to have an idea of what it looks like. But that's how the structure is fabricated, right? There's an additional detail here, which is this defect right in the middle of the Bragg reflector, right, of the corrugated structure, and we'll discuss this in a minute. It's also important to note that for most devices you also have to apply some anti-reflective treatment on these surfaces at the facets of the chip, right? So usually you have additional multi-layer structures deposited on either facet in order for these to transmit 100% of the beam at the Bragg wavelength, because otherwise these two surfaces right here would form two additional mirrors, and you would have an additional cavity which would interfere with the cavity which now is the Bragg, the distributed Bragg reflector itself. You don't want an additional cavity, outside the cavity that constitutes the cavity of the laser itself. So this figure illustrates what will happen, in the case of a DFB laser and a Fabry-Perot laser, which we've been looking at in the previous lectures, for the same wavelength span, right? So ranging from 1.5 to 1.57. So for the DFB, right, for the distributed feedback laser, because the period of the structure is much smaller, usually it has submicron dimensions, right? What will happen is that the FSR of this type of structure will be much larger, as we've discussed before. Whereas for a Fabry-Perot cavity, because the cavity is so large, usually 0.5 millimeter or 300 micrometers, as we've discussed before, so the cavity is formed by these two facets here, which constitute mirrors, right? Because the length of the cavity is much greater than this dimension here, the free spectral range, so this distance here, which is actually the FSR in wavelength, will be much smaller, and therefore for the same wavelength span you'll have many peaks along the gain region. So let's say that this is the gain region, and therefore you have many lines in the spectral response of this cavity, whereas in the gain region you have only one line in the spectral response of this structure right here. Now, by tuning the slab waveguide parameters, it's possible to make it so that it supports only the fundamental transverse mode. Okay, so this is another detail that we have to pay attention to, right? This we've been talking about this transverse mode right here, but this waveguide could support higher order modes, such as I'm illustrating here, right, other than the fundamental. So attention must be paid in order to design the refractive index of this layer and the thickness of it in order to get a single mode waveguide, right? So that's one aspect. So that has to do with the refractive index difference and the thickness of the active region, but that's usually easy to design. An additional problem in DFB lasers is that fact that due to the symmetry of the distributed reflector, it supports two degenerate longitudinal modes, right? So basically these modes correspond to the two directions, two symmetrical directions that the beam of light can propagate inside the structure. So instead of this, what you'll actually have, if you have a perfectly symmetric structure like this, is a response that looks like this, right, along the frequency or wavelength spectrum. If you're talking about spectral power distribution, right, you have two lines instead of one, because these two modes will be degenerate, and since they cannot have the same frequency or lambda, they will split, right? And you will actually have two lines for this structure. And the way to cope with this and guarantee that only one longitudinal mode is supported is to introduce a defect, which we've shown in the previous slide, right here. So usually this right here is the defect in the lattice, or defect in this one-dimensional crystal structure, right? Which is introduced. Usually the defect has a quarter wavelength, and what it will do is to break this degeneracy and guarantee that only one mode is supported by this structure. So the advantage of distributed feedback lasers is that they can have very small line widths, and because of that they are widely used in optical communication systems.